Today we'll be creating a Nastran Solution 111 modal frequency response analysis with superelements. Superelements let you simplify part of a larger structure to help you solve it faster. In order to use superelements, we first need to create an assembly FEM. As a baseline for comparison, we'll first use response simulation to create a frequency response analysis and a sine base excitation analysis. Since Response Sim doesn't support superelements, we'll create a Solution 111 modal frequency response analysis where we can incorporate superelements. Lastly, we'll compare results from all analyses. We'll begin by creating component FEMs for our assembly. Each of the components in our assembly already has a material assigned to it, so we won't need to do that when we go to create our finite element models. We'll be using the hex dominant mesher today for creating our meshes. Here I'll use the lightning bolt to get a suggested element size and cut that in half. And here you can see the results. So we'll continue with the next component. And create a hex dominant mesh on it. And in some cases where it's able to completely hex mesh the part, we won't get any pyramid transitions or tetrahedral elements. We'll just get all bricks. Then we'll continue on to the next component. And create a hex dominant mesh on it. And for all of these, by default, the mesh collector and physical properties are inheriting the material from the CAD model, which we've already assigned materials to. Now, because this component is going to interface with our superelement, we need some 1D element spiders to help facilitate that. So here I'm making point-to-face spiders. These are geometrically associative. So if we have any CAD changes, these spiders will update. And we're going to create 4 of them. And we'll use those later to connect up our components. Alright, we'll continue on to the next component, create a hex dominant mesh on it. And this one's pretty easy to brick mesh 100%. And continuing on to the next component. Again, hex dominant meshing all of them with an element size roughly half of the suggested element size. Alright, now our gimbal support is another component where we are going to be interfacing with the superelement. And here we'll not only create a hex dominant mesh, but we'll also create our spiders. This will help facilitate later making that connection between the superelement and the residual structure. Alright, that looks good. So that's all of the components. Now we have a sub-assembly which we'd like to create an assembly fem from. We'll say map to part and make sure we select the correct CAD part to map it to that matches the name. And since we've already created component fems for all of the components, we'll automatically map them into our assembly fem. Alright, that looks good. Lastly, we'll go ahead and resolve any node and element conflicts with the assembly label manager. Alright, we'll do the same thing for our top level assembly. We'll create an assembly fem, map to part, make sure we've got the right part selected, and automatically map all of our component fems and sub-assembly fems into our assembly fem. Next, we'll create a point-to-face spider that will define our enforced motion location. Alright, next we'll define our interface connection between our superelement and our residual structure. Now, since the connection location is buried within the structure, I'll go ahead and hide our residual structure and we'll just have what will become our superelement later on. We're going to create a node-to-node connection, and I'm going to make it editable. Normally, I wouldn't advocate creating node-to-node connections because they won't update if there's a CAD change. However, for connecting superelements into residual structures, we need to create node-to-node connections because when we replace the base fem with the superelement, we're going to lose any geometry. We're only going to have these nodes defined in the superelement. So that's why we need to make a node-to-node connection. I'm going to use method of connection as proximity, so I don't need to care about the order of selection here. And I'm going to select those 4 nodes in what will become our superelement for our source. Then I'll go ahead and turn on the residual structure that we're going to connect into and select the corresponding 4 nodes in it on those spiders that we created earlier. Here I've made a bad pick. Let's go ahead and deselect all for our target, and maybe if we orient the view a little bit better, we can get that center node on the spider. All right, and here we want to use a C-bush element. Let's go ahead and edit the mesh associated data to specify the coordinate system. And then we'll also specify the physical properties for the C-bush for the stiffness in DOF 1 through 6. All right, that looks good. Let's go ahead and turn on everything. Next, we use the assembly label manager in order to resolve any conflicts between node and element numbers. Now, because we want to maintain the node and element numbers of what will become the superelement, I want that to have 0 offset. But I can't do that right now because the spiders that I've created and 1D elements that I've created in the assembly take up those first node and element numbers. So I'll need to first offset all of those. First we'll get all of the nodes and we'll offset it by the highest node number in our assembly. And we'll do the same thing for the elements. We'll go ahead and modify the label and offset it above all of the other node and elements in our assembly fem. Alright, so now when we go to our assembly label manager, that 0 slot will be available for us to put in a 0 offset for what will become our super element. And the rest of the structure now is resolved. You can see green checks for all of the nodes and all of the elements as well. Alright, so next we'll create our sim. And we'll set up our Solution 103 response simulation. All right, let's make sure we have the check on for random and sine-based excitation events, since we're going to be creating sine-based excitation in just a moment. Let's also limit our structural output requests so that the simulation will run faster. Here you can see we have quite a few outputs selected. Since we only really need displacement, SPC force, and stress, we'll go ahead and turn off force and grid point force. Next, we'll go ahead and edit our Lanczos card in order to get the modes that we need for a good result. And here, because we're interested in a frequency response analysis up to 2000 Hertz, we'll get modes up to 2500. All right, next we'll make some connections between our various component FEMs. We're going to go ahead and glue everything within the super element, what will become the super element. That will connect all of the components in the super element. There you can see it's created 2 sets of glue. And then we'll turn on the residual structure. And because we have some large gaps between the gimbals and not so large between the gimbal mount here, we'll go ahead and first create glue with a fine tolerance between those 2 components. And then for the remaining components, we'll go ahead and create glue, but with a larger tolerance. Because here you can see the large gap there. And 1 millimeter will find that gap there. And similarly between the other gimbal on the inside. So there you can see it's found 4 face pairs and created the glue. Now, just to organize our glue, we'll go ahead and create a folder in our simulation object container that will hold all of our glue. And then we can add the folder to subsequent solutions. And that will simplify adding the glue to other solutions once we create them. All right, next we'll create our enforced motion location, and we only want to enforce motion in the Z direction. Then we'll create a user-defined constraint that will constrain all the other degrees of freedom except for the direction of our enforced motion. All right, now we're ready to solve. And I'll go ahead and pause the video while it's solving, but in the bottom right hand corner of the solution monitor you can see it takes about 1.5 minutes to run. All right, if you don't have the Response Dynamics toolbar on, you can turn it on by right-clicking in the toolbar area. And we can create a new Response Dynamics, select our Solution 103 Response Dynamics, and then select our modes that we've recovered. Here you can see there's 30 of them. And we'll also expand the Response Dynamics Details view, and we can see the total effective mass in the various directions. Go ahead and edit our damping factor. We'll put in a 2% viscous or critical damping. So you can see that's been applied to all our 30 modes. Next, we'll create a frequency response event. And we'll take the defaults. Then we'll define an excitation, which will be a 10G sweep. So here we'll select our excitation node, enforced motion location node, and on the fly we'll create a new function. And here we'll select acceleration for our ordinate. Abscissa will be frequency. And for our XY values, we'll start at 1 Hz, at 10 Gs, and then at 2000 Hz, also 10 Gs. All right, now we can solve for our nodal response. And I'm going to select an arbitrary node on the mirror, but we'll take note of that node number, and we'll be using it for all of our results. All right, so this will be a frequency response. We'll put a prefix of FR on there, and we can plot our function. All right, and there you can see the node number 10501. All right, that looks good. Next, we'll create a sine base excitation event. Here we'll select our output requests, and we are only interested in displacement, so that's the only one we're going to be looking at. And we only want the spectral analysis results. Now here, if we wanted contour results, which we don't, we purely want spectral results, we could select frequencies and groups of nodes that we'd like results at. And here, 10501 is our node of interest. But we don't want to do that under contours. We want to do that under spectral results. So we can turn off any contour results. And here we'll create our group for our node of interest. So that group contains just one node, and we'll use that for our spectral results. All right, for excitation frequencies, we'll take the defaults. And we'll use the same excitation that we had defined earlier for our frequency response analysis. Here we can see that record right here, the 10G sweep. We can plot a preview of it. All right, then we're ready to solve. And this is a real-time solve. This one solves very quickly. And then we can look at our spectral results in the XY function navigator. Here we're interested in the Z response. And we can overlay our result from our frequency response analysis onto that plot and see that they match exactly. Alright, so that is our frequency response analysis. Next we'll create our solution 111 modal frequency response analysis. And here, so we can see our node of interest, we'll scroll down. And for our output requests, we're really only interested in displacement. So we'll go ahead and create a new output request that will have just displacement in it. So here we'll deactivate force, grid point force, SPC force, and stress. And if we preview, you can see now we've only got displacement. And also we only want displacement at that one node. So if we change our sorting to sort 2, we'll get XY spectral results, and we can select that one node that is in our group that we created earlier. Alright, next we'll use the same Lanczos card that we defined earlier in our solution 103 response dynamics. Next we'll define our critical damping at the same percentage as we had in our response dynamics analyses. And then we'll create a modal frequency step. Here we'll take the defaults. Alright, we want to add our glue to our solution 111. So we'll add that to our active solution, just the folder. That will get all of the glue within that folder added to the solution. Alright, next we'll create a fixed constraint at our enforced motion location. Next we'll define our forcing frequencies. We'll specify forcing frequencies modal and select a freq 3 for interpolated between natural frequencies with a lower bound of 1 Hz to an upper bound of 2000. Next we'll define a new load set, frequency excitation set, which will be enforced acceleration. And we'll need to set that before we can type in any values for real or imaginary. So here we'll put 1 for real, 0 for imaginary. And in our frequency excitation set, we also have a load set for our enforced motion. Here we can create our enforced motion load. And DOF3 is the direction that we want, and even though the units say millimeters, it's really millimeters per second squared. That's going to be 10 Gs, 98,100 millimeters per second squared, and we're ready to solve. I'll go ahead and pause the video. You can see it takes about 30 seconds to run, and we can look at our results. So let's plot our results for response at our node of interest in the z direction, and then we can overlay the results that we had gotten from our sine base excitation and our frequency response analysis. And we can see they all match perfectly. All right, next we'll create our superelement from our mirror subassembly. Now we could create a superelement from an individual component finite element model as well, but here we have a subassembly FEM and it works just fine from here as well. So we've created a new sim from our subassembly FEM, and in the sim we'll create a new solution 103 superelement. You can specify the same structural output request that we had made earlier for displacement, SPC force, and stress. We can turn off force and grid point force. So we're left with displacement, SPC force, and stress. Next we'll take the default DMIG OP2 superelement option. We'll leave the default at 500 degrees of freedom, and we'll specify the same Lanczos card with a maximum frequency range up to 2500 Hertz. Alright, so we had created some spiders earlier, and we want to use the center points of those spiders for defining our fixed boundary degree of freedom A set. So here I'll go ahead and pick those points. There's 4 of them for defining our A set. And here, because we're in a new sim, we'll need to create some new glue. So here I'll define it in the same fashion as I did before with the same tolerances. All right, so now we're ready to solve. And you can see the superelement solution takes a little over 30 seconds to run. Now we'll go back to our top level assembly FEM, and we can edit the representation of our subassembly as the superelement. And here we can select that result file from our superelement analysis. You can see it's created in OP2 as well as an _0 OP2. The _0 OP2 is the one that we want. That's the DMIG OP2. And we'll select an approximation of the base FEM and regenerate the FEM representation. So now that we've edited the representation of the base FEM to be the superelement, there are only those 4 A set nodes that remain. Next we'll clone our solution 111, and we'll call it 111 SE for superelement. And we are not able to just simply solve because the group that had the node of interest in it was on the mirror, which is in the superelement. So we'll need to create a new output request for displacement that includes all of the nodes. And also, we're not after spectral results anymore because that would be a lot of plots. So we'll go for our default sorting, which will be contour results for all the nodes. All right, so we're ready to solve. And here I'll pause the video and we'll go ahead and post-process. So here you can see the results at the various frequencies. All the way up to 2000 Hertz. And also we have results for our superelement, SEID3. So to view those results together, once we've loaded both of them, we can say plot with loaded superelements. And you can see the results on the entire assembly for both the superelement and the residual structure. Now, to create that plot, that XY plot, we'll create a graph across iterations, and let's find that node again, 10501. So we'll use method by node ID and select 10501 across iterations, across frequency, and then we can create our plot. Now, the reason why this looks a little bit different is because the axis type is linear. Let's go ahead and go to automatic, which is going to make that logarithmic. And then we can go ahead and overlay our results from our frequency response analysis, our sine base excitation, and our solution 111 with no superelements. And we can see they all match up perfectly. Creating a Nastrian solution 111 modal frequency response analysis with superelements is quick and easy with Simcenter 3D.